over today and tomorrow, we are going to be reviewing factoring and learning a couple of new methods of factoring. And then tomorrow, we're going to do rationalizing. And these two things, everybody, these two things are the most important tools you are going to have available to you in most of the first unit and the rest of the course as well. It's going to keep popping up. You'll be looking at a mathematical expression that you need to simplify. Why? Because it's too complicated to work with. And you'll open up your toolbox and you will either be looking at factoring or rationalizing, one or the other. Might there be other times where you use other little tools? Yeah, but these are the big ones. So what we're reviewing today is how to factor expressions, and then tomorrow we'll do the rationalizing. So I want to review all of the methods of factoring. And most of them are pretty basic, but there are some new ones along the way. In general, and I feel as though I could just wear a button every time I teach this class, a big yellow button that said in general. Because any rule that I give you is always going to be in general, and there's going to be specific examples where the rule doesn't apply, okay? So in general, the following factor methods should be applied in the order listed in order to successfully factor expressions. So 1, always look for a greatest common factor first. And that should be obvious because even though you can leave the greatest common factor for the end, extracting something from an expression makes the rest of the expression simpler to work with. Quadratic trinomials. I'm talking here about simple quadratic trinomials and more complicated quadratic trinomials. Okay. Simple because the coefficient of the quadratic is 1, more complicated because it's not 1. Factoring by grouping, which you were taught in grade 10, but, well, I'll ask, by a show of hands, how many of you remember being taught factoring by grouping? Never mind how it works. Probably very few, because we don't use it very often. A difference of squares, which is pretty obvious, but then there's something called the difference of cubes. And it turns out, everybody, just like you can factor x squared minus 9, you can factor x cubed minus 27. They're both differences. One is a difference of squares. X squared and 9 are both squares. X cubed and 27 are both cubes. And, by the way, can you factor x squared plus 9? No. You cannot factor a sum of squares, but you can factor a sum of cubes. So x cubed plus 27 is factorable. So the last three methods of factoring, difference of squares, difference of cubes, sum of cubes, are, I think, things that you just memorize. I hope you would agree that that's a memorization thing. I don't know too many people that if they were asked to factor a squared, I better not use a's, they were asked to factor p squared minus 16, would think, oh, it's p squared plus 0p minus 16. So I'm looking for two numbers that multiply to give negative 16 and add to give 0. I don't think too many people will do that. Does that work? Sure. But we just know it's p plus 4, p minus 4. Are you with me on that? Okay, well, it turns out that a cubed minus b cubed is a binomial times a trinomial. It's a minus b times a squared plus ab plus b squared. Did I get that right? Yep. And the reason I asked did I get it right is I probably haven't used that since last June. It just doesn't come up anywhere in my life. But it's going to come up in your life again and again and again, so you will remember this. Believe it or not. You're not given this. This is not on a formula sheet. And a cubed plus b cubed is a plus b and then a squared minus ab plus b squared. Just to make sure you understand, that's a 1 There's a temptation for some students to put a 2 there because of how perfect squares factor and stuff. Okay. I want to demonstrate this to you. We don't need to do this. I could say just trust me, but if I said multiply out a minus b times a squared plus ab plus b squared, you're apparently supposed to get a cubed minus b cubed, right? Well, I just want to demonstrate that to you. You would have to multiply that a in the a minus b by all 3 terms here, and the negative b in the a minus b by all 3 terms here. And although I think most of you can handle that, some people may choose to make a kind of a grid and say, I'm going to take my a minus b on the left and multiply by the a squared plus ab plus b squared. So you multiply them like a matrix. A times a squared, a times ab, a times b squared, a squared times negative b, ab times negative b, and negative b times b squared. And you get these 6 terms. But if you look at them carefully, these 2 terms are identical but opposite. And these 2 terms are identical but opposite. So it works. I'm telling you it works. You get a cubed minus b cubed, which is what we're supposed to get. Except you're always going in this direction, not in that direction, right? All right, examples. Factor. Well, this is really childlike in its simplicity. We can take a 2 out. You've all had me as a math teacher before, so I don't need to remind you that if I make a mistake, you need to let me know. And I will. But I take a 2 out. Now I'm looking at factoring this and saying what 2 numbers multiply to give negative 18 and add to give negative 3. That would be negative 6 and 3. And we're done. And I probably, hopefully, don't need to remind you as well, you never, ever do this. You want to see that big vein in my forehead start throbbing? Go left to right. Don't. You go top to bottom. Okay? You always go down. If you run out of room on paper and you hit the bottom, go to the next page or go back up to the top of the next column. So don't do this. It's problematic. Any questions with A? Okay. 6x squared minus 11x plus 3. This is something that even by the time you get to grade 12 in Math 30-1, some students still struggle with. You need to be quick at this. You need to be able to factor something like this. And I realized near the end of last semester in my Math 30 class, I was walking around watching some people, and at least 2 people in the room were using decomposition, which kind of surprised me. But it works. I don't use decomposition. What I do is I say, I need to factor this by trial and error, and it makes sense to me that this needs to be negative 3 and negative 1. Because they have to multiply when I FOIL it out to get that positive 3. And I have a negative term in there somewhere because I have negative 11x. Then what I say is, I'm going to try some things. So first of all, can I try 6x and 1x? I can, but that's not my first choice. My first choice is always going to be numbers and variables that multiply to give the 6x squared that are smaller numbers that are closer together. So I'm going to try 3x and 2x, and I hope that you all understand why putting the 3x here is a dead end. It's because I will have created a common factor of 3 in that binomial, but there is no common factor of 3 in the expression. So if my suspicions are right, this is it, and what I need to do is FOIL it out to confirm that I get the negative 11x, and I do. I don't need to do it on paper. So 8 minus 27r squared. Well, 8 is a perfect cube. 8 is 2 cubed. And 27r, oh, wait a minute. Does yours say R? Yours says R cubed, I hope. I got to fix that in my handout or in my file. So this is the cube of 3R cubed. So I just want to confirm. Yours says R cubed. Okay. So this is a difference of cubes. And we know that A cubed minus B cubed is equal to A minus B, A squared plus AB plus B squared. Well, I know that. You know it by going back to the previous page. Speaking of which, can you do so, or going back to the top of the page, is that the same thing? Okay. So what we are thinking here is that the 2 is A and B is 3R. So this is going to become 2 minus 3R, and then 2 squared plus 2 times 3R plus 3R squared. And that 3R that's being squared inside of the brackets needs to be in its own set of brackets. So we have 2 minus 3R, and we clean this up. We get 4 plus 6R plus 9R squared. Now, this is a quadratic that's in the second set of brackets. As long as there's no common factor you forgot about at the beginning, this is never factorable. It's not factorable. Think about it this way. If this quadratic were factorable, then why would we leave it that way in the rule? We would write it in factored form. It never is factorable, as long as you've taken out a common factor, if one exists. Any questions with C? All right, grouping. Sometimes you have 4 terms, and this goes back to grade 10. How many of you remember this? Not likely, eh? If you have 4 terms and there's no common factor, then you have to try factoring by grouping. Not all 4-term polynomials are factorable by grouping. Not all of them are, but sometimes they are. And what you do is you group the 4 terms into 2 pairs of 2 terms. And it's important that you're adding the 2 pairs. You don't want to do this. This would be an error. And I think you can see why it's an error, because that negative would have to be applied to everything inside, making the 16 negative, and it's not. It's positive. So we have to do this. We have to say plus negative 16z plus 16. To how many of you is this coming back? Okay. Couple. You factor the first pair by using a greatest common factor. I always put the line through my z. That way I don't confuse it with a 2. And then, when you go to extract the greatest common factor out of the second pair, you do it in such a way that you will be left with whatever you had left in the first pair. Coming back now? Okay, more people nodding. So I would say I need to have left z minus 1, which means not only do I take the 16 out, I take the negative out. And now I have z minus 1. And I'm going to ask a question here that I will ask numerous times in this course. Alex, how many terms are in that expression that I've highlighted at the top? 4. Not a trick question. How many terms are here? 4. How many terms are here? 2. Terms are things that are added or subtracted from each other, and each of the terms can have things multiplied together. But what we are looking at here is this minus this. So is there a common factor? Well, yeah, there's a common factor of z minus 1. And I'm aware that many students don't look at it this way. But if I factor out the z minus 1, I will have left z squared minus 16. How many of you, now that it's maybe coming back to you, how many of you would have written those two factors in the opposite order? Okay, and I think that might be how it's taught to you in grade 10 for some reason. But the order of those factors doesn't matter. So are we done? No, because z squared minus 16 is a difference of squares. And we certainly encountered this in 30-1, those of you that have completed it, in trig, where you do some factoring with trigonometric expressions, and then you think you're done, and you go, wait a minute, I can continue factoring. So I can factor this into z minus 1, z plus 4, z minus 4. And as I said, just to finish this one out, not all four-term polynomials are factorable using that method. If they were, then we might be able to get away with doing this more often than the factor theorem for you Math 30 people. But we can't. Any questions with D? Okay, another type, this is more from Math 20. This is quadratic. I know that by the time you hit Math 30, you say it's quartic because it's degree 4. But it is also quadratic. It is quadratic because of these coefficients, or these exponents rather. A quadratic is something that has something squared, maybe a coefficient too, but something squared, plus a number of those things to the 1, plus a number of those things to the 0. We don't normally write this 0 or this 1. But I can factor this basically by saying I can put p squared here and here. And I'm just a little curious. I won't ask, but I'll just say I hope you can see that by putting numbers here and here will guarantee we get a p to the 4 and guarantee that we get some p squareds when you FOIL it out. We just have to figure out which two numbers multiply to give negative 6 and add to give negative 1. And we're done. Can we factor p squared minus 3? Well, no, it's not a difference of squares. Good? Okay. Well, same kind of thing with a common factor. We can take a 2 out and have h squared minus 5h, and have h to the 4 minus 5h squared plus 4. Now I can factor this into h squared and h squared, looking for numbers that multiply to give 4 and add to give negative 5, which should be a piece of cake. Minus 1, minus 4. H squared minus 1 is a difference of squares. H squared minus 4 is a difference of squares. Okay. Again, even though you Math 30 people look at that and see a quartic polynomial function, none of the work we're doing in this first unit needs the factor theorem until those people in Math 30 have learned the factor theorem. Okay. Any questions with F? All right. So now let's talk about greatest common factors. Because up until now in your high school career, all of your exponents on the variables have all been whole numbers, or maybe integers. They've been numbers without decimals, numbers without fractions. So let's just talk about factoring 2x to the 10 minus x to the 7 plus 9x cubed. This isn't a calculus problem, it's really simple. I hope everybody sees the greatest common factor as x cubed. So we would factor out the x cubed, and then we would, well, the way my mind works is I would say that I need a 2x to the 7 in there because 2x to the 7 times x cubed is 2x to the 10. How many of you think that way? How many of you take 2x to the 10 divided by x cubed? A couple, okay. I would have to write in here minus x to the 4 because the way my mind works, x cubed times x to the 4 will give me that x to the 7. And then I would put 9 here because 9 times x cubed is 9x cubed. No problem. I'm going to write that as plus 9x to the 0 to make a point in a minute. So no problems, but let's make some observations here. The first observation is, why was x cubed the greatest common factor? It's because 3 is the smallest degree on all of the variables. Right? You look at all 3 of those variables, and they are raised to the 10, they are raised to the 7, they are raised to the 3. X raised to the smallest exponent will be in the greatest common factor, if it's x. So that's the smallest degree. Secondly, the exponents inside the brackets add to the exponent on the x cubed to give the exponent that we started off with. Okay? And I know this is obvious, but it's not going to be in a second. What I'm telling you is the reason we put a 7 here was because 7 plus 3 gives you the 10. The reason we put a 4 here is because 4 plus 3 gives you the 7. And the reason we put a 0 here was because 0 plus 3 gives you the 3. And none of this, in factoring this, requires this deep level of thought. It doesn't. In fact, you're probably a little bit more confused now than you were when you just were asked to factor it. That's fine. But how do you factor this then if I don't explain all that to you? And it turns out that not only does this factor, it simplifies very nicely if you can factor it. So first of all, I hope you would agree that there is a greatest common factor for sure because each term has a coefficient that contains 3 as a factor. Okay. Each term contains x's. So that means we will be able to factor x's out. What exponent on the x do we factor out? The smallest exponent. And when you look at a number line, negative 1/2 is smaller than positive 1/2. So we're going to factor that out. What do we have left? Well, we factored the 3 out, and now follow along carefully. And some of you will pick up on this in lightning speed, and others will struggle. That's fine. We're here to practice and get better. It will contain x, and don't draw this thing. I'm just doing this. Raised to an exponent that when added to negative 1/2 gives me negative 1/2. So what do I add to negative 1/2 to get negative 1/2? Well, I get 0. And I think most of you would have said, well, isn't it to the 0 anyway because we factored it out? And that's fine. In fact, I think many of you would have just said this, wouldn't you? But I want to write x to the 0. Minus 2, and I now have to write x raised to an exponent that when added to the negative 1/2 takes me to the exponent I started off with. And I'm a big fan of number lines. I know the answer is 1 because I look up here. I'm figuring out what do I add to get from negative 1/2 to the exponent I started off with. And I can see it's 1. If you don't know that from negative 1 to 1, negative 1/2 to 1/2 is 1 by thinking of a number line, I don't know. I don't know what to say. I think we all know that. So this will be 2x to the 1. And if you wanted to, you could multiply this out to confirm that you'll get 3x to the negative half minus 6x to the positive 1/2 when you add these exponents. So we end up with this. Now, of what value is that? And I do want to talk about this. This isn't just an exercise of how to factor. First thing is, we don't like negative exponents. It's not that we don't like them. They're not useful in calculus. However, this is useful. And in calculus, we will be interested in, a lot of the time, with the answer to these two questions. More specifically, we are interested in where an expression equals 0, where the top of this is 0, the whole thing equals 0. We are interested in, a lot of the time, where is this expression equal to 0? But we're also interested in where the whole thing is undefined. Turns out that an expression in calculus being undefined is sometimes just as important as when it's 0. Okay? So you need to get it into this factored form, and now I can look at it and say it's equal to 0 at 1/2, and it's undefined at 0. And that is not obvious looking at the original expression. Even if it is, it won't always be obvious. So any questions with that example? All right, one more. So in this expression, which is a binomial, it has two terms. Each term contains a base of x squared minus 1. So we are going to be able to factor out x squared minus 1. Raised to what exponent? Well, the lowest exponent, which is negative 1/2. So what do we have left? Well, out of the first term, we're going to have x squared minus 1 raised to an exponent which, when added to this negative 1/2, will give you this exponent, which is 0. Minus x squared minus 1 raised to an exponent that, when added to this negative 1/2, gives you 3/2. Now, how many of you know what it is? If you don't, you draw a number line. That's my advice. You say, I want to go from negative 1/2 to 3/2. That's like going from negative $1 to $3. You have to add $4. So this is 4/2, which is 2. The x squared minus 1 to the negative half should probably be written as x squared minus 1 to the half on the bottom. I know, by the way, that this entire expression, what we started off with, is undefined when x is 1 or negative 1, because that would be values of x that make the bottom 0. On the top, I have 1 minus x squared minus 1 squared, which is a difference of squares. Look at the bigger picture. This is not math 10 or 20 or even 30. It's not x squared minus 4 that's going to be the difference of squares. It's anything squared minus anything squared. We have a difference of squares. So it will factor into 1 plus x squared minus 1 and 1 minus x squared minus 1. Is everybody fine with that? Nobody is not fine with that. Absolutely. Even at this level, you can make that mistake. Which is, when you look, I'm not saying this to scare you, I'm saying it to prep you. When you look at the volume of work involved in some of these problems we will do this year to get to an answer, if you forget a set of brackets at the top, not only do you not get the right answer, it just gets uglier and uglier and uglier and frustrating. So we need those brackets. What I get here is x squared, 1 minus 1 is 0, and here I get 2 plus x squared. Nope. 2 minus x squared. 1 minus negative 1 is 2, and then we have minus x squared. So I want to, we're done. Are we okay with that? I want to kind of bring this to a conclusion by telling you that this expression equals 0 at 0 and plus or minus root 2. And we can see that, I hope, by looking at the top. If x is 0, x squared is 0. If 2 minus x squared is 0, then x is equal to plus or minus root 2. And we can see it's undefined at plus or minus 1. And you could certainly write the denominator here that way. But I would ask you this question. I want you to think about it. Because to me it makes sense, but you might think differently. There's nothing to be gained by writing it this way. Because we already know x squared minus 1 is x plus 1, x minus 1. Why would we waste time writing it that way? Unless something canceled. So on page 3, 1, 2, and 4, I also have, just in case somebody needs practice with trinomials, on the next page, that whole page of trinomials. You don't have to do it. But, and I hope nobody's having troubles with those. But if you do, you need to clean it up.